Jülich. He's a postdoc working with the SDL AML lab team at the Jülich Supercomputing Center, and his research focuses on the geometry of neural networks through learnable structures. So in his talk, he will present polynomial, trigonometric, and tropical activations.
Thank you very much. So we are going to try at least to answer this question. Which function? Sorry. So we are trying at least to answer or give elements of answer for this question. Which functions can be used as activations in a deep neural network? So in these questions, we are looking for functions, and a principled way to look at functions is through the lens of Hilbert space. So a Hilbert space generalizes the notion of Euclidean space. So you need an inner product, which is complete, and some examples, for example, here you have the Euclidean space, R2 or R3 are special case of Hilbert space, but for functions, for example, you might decompose your function in an infinite sum. And for example, if you take this inner product, the suitable basis you are looking for to decompose your functions is through the polynomials of Hilbert. So polynomials of Hilbert are defined as such. It's a little bit scary, but at the end of the day, those are really just polynomials, and they are orthogonal to each other. So here you have Kronecker delta for orthogonality. So this leads me to introduce our first activation, which is the Hermite activation. And we define it as a weighted sum of Hermite polynomials divided by a certain factor. The factor is not important, but it's for theoretically, but as long as the series converge, you are fine. But for numerical purposes, maybe k factorial is a good choice. Also, if you sample your data from uniform distribution, the suitable basis, and you might be familiar with, is the Fourier basis, which is called cosine and sine. And this leads us to our second activation, which is defined as the first one. So in this question, the second part is deep neural networks. And in deep, the emphasis is on deep. So you know this neural network, and this is a transformer. And another kind of deep neural network, which was previously used more, is convolutional neural networks, so ResNet, or more recently ConvNext. But all of them share this block, which is an MLP, and which is matrix multiplication with weights, plus an element-wise activation. And here, in this case, it's ReLU or GLU or CLU, etc. So in what follows, we will explore learnable orthogonal basis functions decomposed in an orthogonal basis. And yeah, so training with polynomials and trigonometric polynomials is sometimes difficult. And why is this? Mainly due to numerical instability. So if you have a term as x to the power n, this could lead very rapidly to a non or to decay very rapidly. But a way to solve this problem is, and here we got the inspiration from this paper, which is really famous, and which is the paper that introduced the classification ResNet model that classified ImageNet at a level surpassing human level performance. And this paper, the idea of this paper is could be summarized as follows. So the output signal of your MLP block should have the same variance roughly as your input. And since you are doing back propagation, you want your gradient to have the same property. So we want to enforce that the gain remains equal and equal to 1, because we want to stack many blocks of MLPs. So how you do this? You compute a gain, and here in this computation, the most important part is the moment of order 2 that relies on the activation. So it is interesting to note that for the ReLU, for example, the moment of order 2 of both the forward and backward, so for the function and its derivative is equal and equals 1/2. This is, for example, why in PyTorch, for example, you have this square root of 2 in the k-mean initialization that accounts for this to normalize this variance. So if you apply the same idea on Hermite activation, one way to choose those coefficients is the following. So you initialize every coefficient to 1, and the first coefficient is 0 to this formula. But if you take a high degree, this amounts to initializing everything to 1, and this gives you equality in gains. And furthermore, so an important fact of the orthogonality is that it permits this mathematical computation. So the orthogonality helps here to compute the moments of order 2. And you could divide it by the gain you get. So in order to have unitary gain here, square root of e. The same goes for Fourier activation. And here the constant is a little bit different. So now I have introduced 2 activations based on orthogonal function space. And now let me introduce another kind of algebra, which is the tropical semi-ring. So you take addition and so you take multiplication and you replace it by addition, and you take addition and you replace it by max. Obviously, the power becomes a multiplication, and this gives you a structure of semi-ring where you could define a tropical polynomial, which is this following. And we define the tropical polynomial activation as such, which is the tropicalization of a polynomial. And if you paid attention from the beginning, the square root of 2 is the same as for ReLU. And in fact, this activation generalizes ReLU to a higher degree. They are not orthogonal in the traditional way, but they are orthogonal with respect to the proximal operator. Initialization is the same for preserving variance. So a first remark is that all of those activation and classical activation could classify data. They do it differently, very differently, as you can see, but they classify well. So we pre-trained a large model, so for example, convexity on ImageNet classification task from scratch using this variance preserving scheme. And here you see the mean of the accuracy, and we did this over 3 different seats. Same for GPT-2 model, and each time we replace the activation GLU by the learnable activation or orthogonal activation we have on OpenWebText for next token prediction. So you could fit a classical activation with those activations. It's really easy. It's a classical approximation theory. And you should pay attention to the degree, so you should have enough degree to do it on the interval you want. And sometimes, for example, for Fourier, there is this aliasing effect that might occur. But if you fit the function and its derivative, which is called a Hermite interpolation, everything goes well. And finally, for the tropical activation, so in general, there are convex, so you cannot fit non-convex functions, but if you extend to tropical rational function with the tropical rational quotient, then you could fit anything as well. So we did this trick to fine-tune. So we took a model that was pre-trained on GLU, and we fine-tuned it by fitting those coefficients, and then training for other epochs, and this gives good results on SAFA. The code of the approach is really simple. It is integrated in PyTorch, fully differentiable, and you could use it as such. So in terms of flops and parameters, those are negligible. It's like for n extra parameters for Hermite activation. However, for memory, the activation's memory scales by an order of n, which could be problematic. Also, the training could get slower, but there is also room for optimization for this kind of activation. Inference remains fast. So in conclusion, I have presented a principled way to look at activations through the lens of Hilbert space and tropical geometry. Some natural extensions are via wavelets, for example, or rational functions, as in Young and Wang 2024. It seems that low degree is needed for natural language processing and tasks of image classification. We don't know for other types of data which happens. Also, those still require a batch norm or a layer norm. So, but we were successful in removing them from the model for small scale training. And I want to remind you that those are only for initialization. So we studied the initialization and not the training dynamics. So we don't know how the back propagation should be adapted for these kinds of activations, or if it should not. So thank you for your attention. My name is Ismail Khalfaoui Hassani, and this work was done under the guidance of Stefan Kesselheim from Forschungszentrum Jülich. Code and paper are accessible via those links, and I would like especially to thank my team in Forschungszentrum Jülich Simulation and Data Laboratory Applied Machine Learning. Thank you for your attention.
Thank you. Any questions? Come to the microphones. So I have a question. So you showed some benchmarking results in terms of computational costs. Did I get right that this is scaling linearly?
Linearly with the degree of your activation. So for all of them, you could make it scale linearly with the activation degree. For Hermite, for example, if you use the parallel form, it scales quadratically, but there is a recursive form which is good for Hermite polynomials that could make everything linear. So all of them scale linearly with the degree you want to achieve.
Okay, impressive. Any more questions? Then let's thank him again.